In previous sections, we learned several integration techniques, such as integration by substitution, integration by parts using trigonometric identities, and splitting apart rational functions by partial fractions decomposition. In this section, we want to take a look at strategies for identifying which technique is appropriate under certain circumstances. We're not learning any new information necessarily, rather, we're learning how to apply the information that we've already seen. In previous sections, we knew exactly which technique we were to use on an integral because of the context. But in general, we could have integrals where we need to figure out which technique is most appropriate. So that's our goal for this section, to understand when certain techniques are appropriate. Before we talk about that, let's review an important perspective that we've talked about before. Let's think of the difference between derivatives and integrals. Taking derivatives is a process. We have derivative rules that we follow. We just apply those rules, and we can take the derivative of any function. On the other hand, solving integrals is an art. There's a technique to it. It takes practice and development. We have differentiation rules, chain rule, product rule, quotient rule, all those different rules, but we have integration techniques. When we're taking derivatives, we just follow the rules and we'll always find the derivative. When we want to find antiderivatives, it's not always quite so straightforward. We might have to use different techniques. Some techniques we might try that don't actually work out, and we have to try a different one. So integration often involves trial and error. And this isn't very exciting to think about, but oftentimes we'll have multiple failed attempts for any given integral. So we don't want to get discouraged. That's just part of what integrals are. They're different animals than derivatives. The key to building intuition and getting better at solving integrals is practice. And I know this sounds cliche, but really the way to get better at integration is to try to do a bunch of integral examples. So let's talk about some strategies for identifying which integration technique would be most appropriate. So we can imagine that we've got some integral and we're trying to figure out what technique to use. The first step would be to simplify the integrand. If we see a way to simplify, we want to do that. The next step is to look and see if we can find an obvious substitution. Integration by substitution is a good default technique. It's the most common technique. It's the most important technique. Many problems that use other techniques will also include a u substitution, so we want to check first to see if we can just do substitution. All right, what if we don't see a straightforward substitution? Well, then we want to try to classify the integral, thinking about the different forms of integrals we've seen. We've seen rational functions, we've seen trigonometric functions, and we want to try to think if we can classify the specific integral that we're working with. So if we have a clear inner function whose derivative appears somewhere else in the integrand, then we can likely solve that with u substitution. If the integral involves the product of polynomials and transcendental functions, polynomials could be something like just x or x squared. Transcendental functions are exponentials, logarithms, trigs, sine of x, something like that. If we see that sort of a product, then that's a suggestion that we should try integration by parts. Often that technique will be effective. If we have a rational function, almost all the time it will be partial fraction decomposition. Finally, if the integral involves only trig functions, such as powers of sine or cosine, then we will likely have to use some trigonometric identity to simplify. Now, as we think about a specific integral problem and try to strategize which technique is most appropriate, we might have to use multiple attempts, and we might actually have to use several different techniques in the same problem. We might try several before we land on the correct technique. So we want to stick with the problems. The more we practice, the better we'll build our intuition and the more proficient we will be. Let's take a look at some examples. Now, as we work through these examples, we don't know which technique is the most appropriate. So we need to be thinking about substitution, integration by parts, partial fractions, trig identities. We need to identify which technique is the best. And I strongly encourage you, as we work through these examples, to pause the video before I work through the solution. You see if you can get to the same solution. If you get stuck, that's okay. You'll still be learning from it, and it will be very effective to help you master the integration techniques. So let's take a look at example 1. So for example 1, we have a product. We have x, which is a polynomial, times natural log of x, which is a transcendental function. That tells us that probably integration by parts will be the technique to use here. Now with integration by parts, we had an acronym for choosing u. It was LIATE. We need to choose part of the integrand to be u, and the remainder will be dv. And the way to choose u is to think of LIATE. L stands for logarithmic, I inverse trig, then we have algebraic, trig, exponential. This LIATE is only for integration by parts. We don't use this acronym when we're doing u substitution. All right, so I have a log function. I'm going to choose natural log of x to be u. Once I have chosen u, everything else by default is dv. So dv equals x dx. I take the derivative of u. The derivative of natural log is 1 over x. I take the antiderivative of dv. The antiderivative of x is x squared divided by 2. Now I use the integration by parts formula. I have u times v minus the integral of v du. U is natural log of x. V, x squared divided by 2, minus the integral of v, x squared divided by 2, times du, 1 over x dx. I can cancel a power of x, and I have the integral of x divided by 2. So this turns into natural log of x times x squared divided by 2, minus 1/2 times the integral of x, which is x squared divided by 2. We add a plus c, and we have our answer. Let's take a look at example 2. Example 2 looks fairly similar. We have the integral of the natural log of x divided by x. So we might be tempted to try integration by parts again, and that could work, but there is a better method. I'm noticing that natural log of x has a derivative of 1 over x, and I have a 1 over x in the integrand. So I'm going to think of integration by substitution. I will choose u to be natural log of x because the derivative is 1 over x. So I take the derivative, I solve for dx, dx equals x du, and now I'm ready to substitute. I have the integral of u divided by x times dx, which is x du. The x's cancel, and I'm integrating u. Well, the antiderivative of u is u squared divided by 2. Replace u with natural log of x, and I have natural log of x squared divided by 2 plus c. We should think of checking each of these. If we think of taking the derivatives here, we'll get back to what we started with. Let's take a look at example 3. Here we have a rather complicated looking integral, and I think the first step that we should try here is to simplify. Notice we have a sum in the exponent. So I can break this apart by multiplying two common bases together. This is the same as e to the x times e to the x. If I were to combine, I would add the exponents, and that's what I had to start with. So I can simplify like this. Now, notice e to the x in the exponent can be thought of as an inner function, and the derivative of e to the x is right there. So this is going to be integration by substitution. We'll choose u to be e to the x, and then follow through the steps for substitution. The derivative of e to the x is e to the x. Solving for dx, we have dx equals du divided by e to the x, and now we substitute. I have the integral of e to the x times e to the u times dx, which is du divided by e to the x. Now, you might be wondering here, why did I replace this e to the x with a u, but I left this one as just e to the x? Why didn't I rewrite this e to the x as u? And the answer is I could. I could write this as u. I could also write this as u. Those would cancel, and the problem works out the same either way. I can either leave these as e to the x or write them as u. It doesn't actually matter. But in any case, the e to the x's cancel, and I have the antiderivative of e to the x, e to the u. That is e to the u. Replace the u with e to the x, and we have the final answer, e raised to the e to the x plus c. If we take the derivative using chain rule, we'll get back to e raised to the x plus e to the x. Let's take a look at example 4. we have the integral of sine cubed of x times cosine squared of x. We only have trigonometric functions here, so we should probably use trigonometric identities. And this is one of the special forms that we saw before. We have powers of sine and cosine, and when we have powers of sine and cosine, we try to find the odd-powered trig function. So that's sine. We are going to take away one sine. So I have sine times sine squared times cosine squared. Then at this step, I'm going to use the Pythagorean trig identity. Sine squared of x equals 1 minus cosine squared of x. So I rewrite sine of x times 1 minus cosine squared of x times cosine squared of x. Now, this simplification seems a little arbitrary. Why do we rewrite the function like this? What does this do? Well, remember that the whole purpose is to get to a point where we can do a u substitution. At this point, we can choose u substitution. I'm going to choose u to be cosine and then work through the steps. The derivative of cosine is negative sine. So solving for dx, I get du divided by negative sine of x. Now I can substitute. And the reason that we did this simplification is so that the substitution works out, something's going to cancel with this sine. So I have the integral of sine of x, 1 minus u squared times u squared, cosine of x is u, and then dx is du divided by negative sine x. The sine of x's cancel, and I have a negative here. I'm going to go ahead and use that negative to switch the signs inside the parentheses here. So this is the integral of u squared minus 1 times u squared du. Once again, I switched the order inside the parentheses by just multiplying the negative through to both these terms. So these both become negative of what they were, and I have this. Now, at this point, it's a little bit tempting to just find the antiderivative of u squared, find the antiderivative of 1, do another antiderivative there. However, when we're taking the antiderivative of a product, we can't separately do antiderivatives of the two different factors. There's no rule for integration that allows me to do that. So in order to continue, I must first distribute the u squared into both the terms. So this is u to the fourth minus u squared du. And now we can integrate. Because we're adding in the integral, we can integrate separately now. U to the fifth divided by 5 minus u cubed divided by 3. The final step is to write everything back in terms of cosine. U equals cosine of x. So the final answer here is cosine to the fifth of x divided by 5 plus cosine cubed of x divided by 3 plus c.